What's up to you all awesome and wonderful matriculants? It is that time again on a lovely Tuesday where we learn more and learn extra on your physical sciences. My name is Abram and today we have a nice show with Tracy. Tracy?
Siyabona.
Yeah, Tracy.
Kunjani?
Mkhona wenu njani?
Kikhona.
Nice one.
See, I'm learning.
You are learning.
I am. It's important. You know, and we think it's important because this is also saying no to xenophobia.
Exactly.
We don't agree with it.
We're all Africans, guys.
Absolutely, even if some of us don't agree with the African sun, but let's not go there. All right, there's nothing much I can do about
But
that.
we are all one after all.
We
and
are.
talking about oneness and one
Yes.
family, what are we doing together today?
Today we're doing work, energy, and power. So we're going to look at work and energy, and they said work energy theorem. So we're actually looking at work, energy, and power. We're going to look at specifically work energy theorem a little later on. Some of you may have done it, some of you may not have. All depends on how you teach, you know, where your teachers are at. I haven't done it yet with my learners, but it's okay. Just stick with it. It's good.
All right,
Yeah.
guys, to be part of this show, it's very simple. Like our Facebook page, facebook.com/LearnExtra, XTRA, that is our extra. And make sure that you also follow us on Twitter @LearnExtra. I'll read some of your comments, your questions, so do make sure that you send them through, guys. Get your friends to be on our Facebook page, your teachers as well, guys. Don't be selfish. Let's spread the word out and be a caring family. I've already posted the notes for you because I love you guys and I don't want you to miss out on any of the notes that Tracy is busy on. And talking about those notes, you can get yourself this awesome workbook. It has all the notes and the questions. You can get it for only 139 Rand, guys. So tell your parents to buy it for you. And I know you also have money, so make sure that you get it by inquiring send an email to sales@mindset.co.za and they'll get back to you.
All right, the workbook's so important. Out of all there's lots of study guides and workbooks on the market, but at least this is just one. It's not like some of them are split, so you have physics and the chemistry, and it covers some grade 11 work from last year, which is actually quite important because that's what you guys forget, is that your exam includes grade 11 work. So
it's a must-have.
Yeah, and the exercises will keep you busy for a long time. At least 2 hours on each chapter, which is what you want. You want that.
Yeah, of course.
Good exercises to get it
course.
going. So should we
And
get
with the answers.
teaching?
Yeah.
Okay, there we go. All right, so guys, what we're going to do today is we're going to look at some important definitions because that's quite important in this section. We are going to talk about the work energy theorem. We are going to look at the conservation of mechanical energy just a little bit, and we're going to just briefly do power. It's quite an easy section. So the first one, oh, it's a bit blurred there, but it's all right. Work. You've done work a lot. You did work in grade 9 maybe a little bit. You did a little bit of in grade 10 maybe. But work is done on an object when the object moves in the same plane. And there's where things get a little sticky sometimes in terms of the same plane. What that means, guys, is that when you push an object, the object must go in the direction of the force. So I can't push an object sideways and then the object goes vertically, then we're not doing work, all right? And my best example of this, for example, is when you carry your school bag, even if you have one that you put over your arm. So you do work when you pick it up because it's moving in the direction. Then you put it on your shoulder and you move. Now, ignoring the forward, just going forward, but you're exerting a force on your bag upwards, but your bag is actually moving sideways. So in reality, you're doing no work whatsoever when you're carrying your school bag. Now, doesn't that make you feel excited? Anyway, so work, the equation is F delta X cos theta. F is force, okay, force which would be in newtons. Delta X is the distance it travels, so that's in meters. And theta is the angle of the force to the direction that the object's moving in. Okay, so this is an angle. Now, theta can be anything from 0 to 180. Okay? Hopefully, most of the time, you're going to use 0 or you're going to use 180 or you're going to use an angle between 0 and 90. Okay, you don't really want to use an obtuse angle at all. Okay, now work, which is W, measured in joules, is a scalar. That means you cannot have a direction to work. However, this is one of the only scalars that you're going to use that can be negative. Okay, all negative work means is that there is a decrease in the energy in the system. Okay, so please don't get too worried about whether you get a negative answer. Sometimes you do have to get a negative answer, particularly when you're talking with friction, so don't stress too much about it, okay? We'll get there. Now, to calculate net work, there's two ways you can do it. You can either apply W equals F delta X cos theta to each of the forces you have, and then add all those works together, or you can first calculate the net force. My preference is to calculate net force first, because it's much easier to calculate net work first than to try and have to remember where all the angles go with the work, and then you get confused that way. So I much prefer calculating net work first and then net force first and going from there, okay? Then, work energy theorem. Now, if there's anything that you're going to hate, it's this. Grade 12s, you are going to get work energy theorem, okay? It's one of those sections which the examiners love. The work energy theorem states for us that the net work, important statement, done on an object by a net force is equal to the change in the kinetic energy. So I've written it as EK final minus EK initial, all right, because change in, it's always final minus initial. However, you could say that your net work is equal to change in kinetic energy, okay? Now listen here as well. You have to use net. If you don't have W net and you just put W equals, you will lose a mark, okay? And you got to be careful. They could even go as far as to give you naught, because work doesn't equal change in kinetic. Net work equals change in kinetic. Okay, so be careful here. Plus, on your information sheet, it's going to say W net. So please, grade 12s, don't lose marks on something stupid. Now, remember, kinetic energy, EK, is a half mv squared. Okay, now when net work gets done on an object, the kinetic energy of the object must change. That doesn't mean it has to speed up. It can speed up or it can slow down, but it must change. Okay, this is valid for systems which are conserved. In other words, this is valid for if I throw an object and I'm looking at something that's moving up and down. Gravity is a conservative force. It doesn't change mechanical energy. As soon as I add in a non-conservative force, like friction, things get fun, okay? A non-conservative force means that the mechanical energy of my system is going to change, okay? This is very important here. So this means that mechanical energy will change, all right? I'm going to talk about what that is in a second. And now we get another equation. I've just realized I did this with a lowercase, that should be capital W. Work done by the non-conservative force NC equals change in kinetic plus change in potential. And remember, potential energy is equal to mgh. So it's got to do with height. Guys, work done by the non-conservative force is something like work done by friction. That's the non-conservative force. Okay? Please, you may not do these questions using any other equation. They are very, very, very strict about this. Okay? And you have to use NC. Once again, you can't just put W equals, because then you're saying work equals change in kinetic energy plus change in potential, but it's not. Work is equal to force delta X cos theta. This change in kinetic, change in potential is a specific force. It is friction. It's the work done by friction, not against friction. Please be careful. This is work done by friction. Okay, that's not even, doesn't even vaguely look like friction. I'm having a bad spelling day, by the way. There we go. Now it looks like friction, almost. Okay, work done by friction, and this will be negative. Friction cannot give me a positive work, okay? Has to be negative because friction always takes energy out the system. Always, always, always. Remember, friction opposes motion. Friction in these cases does not help us. We don't like friction. Okay, so in terms of energy, law of conservation of energy, you've been doing this since you were knee-high to a grasshopper. Okay, conservation of energy always states to us that energy cannot be created or destroyed, but simply transferred from one form to another. Now, that's never going to change. However, when we look at mechanical energy is the sum of kinetic and potential. Mechanical energy can only be potential and kinetic. Okay, so I've got E mechanical, potential plus kinetic. All of those are measured in joules. Scalars, we don't worry about direction, but any system, if I'm looking at mechanical energy, I must add the kinetic energy with the potential energy. Okay, even if one of them is 0, it doesn't matter. That also then means that we get to this statement. In an isolated system, no friction. In other words, only conservative forces are around. Mechanical energy is conserved. That means when I take the sum of my mechanical energy initially or at the top of a motion, it must be equal to the mechanical energy at the bottom. We use this equation when we're dealing with things like pendulums, which then swing, and they want to know how fast it's going or how high it goes up at the top. Okay? So this is where we would use this concept, okay? Please, you may never say EP at the top equals EK at the bottom. Never, 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 never. I do not care what your teachers have told you. I don't care what you've read. They will give you naught, okay? You have to start from this. You have to have one of those two equations at the beginning. There's no exception. If EK and EP happens to be naught, you substitute the 0 in the next line, okay? All right, so that brings us to power. Power is the rate at which work is done. So it's W over delta T. W, work measured in joules, delta T, time measured in seconds. That's a capital P, that's power. It's measured in watts. Okay, because it's named after a scientist, it's a capital W. So in this section, we have lots of W's everywhere. It's wonderful. But these capital W's are why you can't use a capital W for weight. Could you imagine if we put another capital into the system? It would just be too much, okay? You've done this equation before. It's part of your grade 9, or it was part of your grade 9 curriculum. So work over time, nice and easy, but sometimes this doesn't help us because we don't know what the network is, okay? Or you have an object that's going at constant velocity, which then means there's no network done, and work is 0, so then we think there's no power, but that can't be true, because if you're riding a bicycle up a hill and you're going at a constant velocity, you are absolutely you as a person are exerting a force, so you as a person are doing work, so there's got to be power somewhere, right? So we have another equation. When something is moving at constant speed, okay, we can work out the power by looking at the average velocity and the force. Now this force must be the force that's giving us the average velocity. Okay, so that force must be, so if I'm riding a bicycle, it's me pushing on the bicycle. Okay, it can't be the friction, it can't be any of those other things, it's me pushing on the bicycle. Okay, that's where it comes from. But note here, grade 12s, where you can add average power. Okay, so it's average power, not full power. The reason why it's average is because we're looking at a constant speed. We're not looking at the acceleration before and after to get the thing moving, so it's average. And we then use average velocity, but the hint here, okay, constant speed must be constant. And I think, you know what, when you're good at timing, you're good at timing, because we need a break, and then we're going to dive into the questions.
Oh, nice one. Well, guys, as we take this break, remember we've got an awesome competition. If you think you are a future star, you've got what it takes to change your future and the future of people around you. Enter the Future Stars competition. More details will be on our Facebook page. There are great prizes to be won. So don't miss this opportunity. Believe it, do it, and write on it. Be yourself. We'll see you after this. Welcome back, guys. If you just joined us now, where have you been? Tracy has been flowing. Make sure that you catch up right now. Get your notes on our website, learn.mindset.co.za, and also check out our schedule and some videos of the past shows that we've heard. But for now, Tracy, I've got some cool comments from
Brilliant.
the Mindsetters.
Okay, let's go.
Let me start on Twitter.
Yes.
It's tskills007. She's always on Twitter. Like even
Okay.
yesterday, big shout out to you. She's watching the show and saying a big shout out to everybody that is watching. So a big shout out to you, underscore skills
Wow.
007.
Okay.
That's cool, hey? You should call yourself
T-skills.
Tracy underscore
Brilliant.
brilliant. Okay.
Insane, mad, crazy, whatever. Yeah, let's not go there. All right, moving on.
All
Yes.
right, let's get on to some questions and comments
Yeah.
from the Mindsetters. Lol, I think I must apply this formula and always meditate before I write my exams. So that was Tracy meditating before the show.
Yeah.
Palisa Simi says, I absolutely love Miss Tracy. Thanks for the effort Mindset does to reach out to us as grade 12s. I'm tuned in and I'm loving the show. Thank you, Palisa.
Absolutely.
Sfiso John Siloma, lovely show. I'm watching with my mom.
Oh,
Nice
that's
one.
so sweet. I love it. Go, Mom. I like that.
Awesome. Grace Masilela says, I love this topic. Though I have some problems, I'm happy Madam is there to help me understand much better.
Oh,
And a question for you.
yes, let's have the question.
Boitumelo Mpali says, why is work a scalar when it is a product of two vectors? My teacher said that it might be said that a vector multiplied by a vector, it is a scalar. But I'm still confused. Please help me.
That's a difficult one, and that's actually first year physics. But an easier way to think about it is in maths, you learned like when you have a positive number times a positive number, you get a positive number. And vectors and scalars work the same. So vectors, if you want to think of it as two vectors multiplied together like you multiply two negative numbers together, you get a positive number. So two vectors multiplied together always give us a scalar. It's very complicated. It's first year varsity stuff, but your teacher's 100% correct that two vectors multiplied together always give us a scalar. But as an analogy, it's like positive and negative numbers multiplied together. And in first year physics, you'll do whole dimensional analysis, and you'll do all sorts of weird and wonderful things with it, and it'll hopefully start to make sense. But it's okay. It's a scale. It doesn't need direction. That's all we need to know.
All right,
Yeah.
last one. Nomatam Sangma says, how do you know if mechanical energy is conserved or not in an object?
Okay. Depending on the question, so they can either ask you to prove mechanical energy is conserved, or they'll tell you in the question that there's no friction and there's no air resistance. Then mechanical energy is conserved, okay? So as soon as there's no friction or air resistance, the mechanical energy is absolutely conserved. If they ask you to prove it, then it's like inelastic collisions in momentum, where you have to take the mechanical energy before something happens and work it out, and then take the mechanical energy afterwards, work it out, and then compare the two. So it depends on the question. But in the question, if they say no friction or air resistance, then absolutely mechanical energy is conserved.
Awesome.
We good?
Yeah,
Okay.
we're good.
So let's do a question. So this will probably help a little bit because it is a swinging ball. A steel ball of mass 0.5 kilograms is suspended from a string of negligible mass. Guys, they just do the negligible mass of the string just to make our calculations easier. It is released from rest at point A, as shown in the diagram. As it passes through point B, which is 0.6 meters above the ground, the magnitude of its velocity is 3 meters per second. So I'm going to put 3 meters per second here. Ignore the effects of friction right there. And I'm not even going to try say your name, Sweet Pea, because it had an X in it. All right, the tongue doesn't do it. All right, this tells me mechanical energy is going to be conserved because I ignore the effects of friction. So no matter where I look at the energy in my system, okay, mechanical energy is constant. So now that gives me the first question. Write the principle of conservation of mechanical energy, in words. The total mechanical energy of a system in an isolated system, don't forget that, in an isolated system is conserved. Done. Okay? All you need. It's nice that we like these small definitions. Now they say to you, calculate the mechanical energy of the steel ball at point B. So now we go back to point B and we go, I know the height, I know the velocity, and I know the mass. So at point B, I'm going to go, well, I want mechanical energy at E mechanical at point B is going to be the potential at point B plus the kinetic energy not at point A, that's just silly, at point B. Okay? And remember, potential energy is mgh. Kinetic energy is a half mv squared. Okay, so now we put in what we know. They said to me that it was a mass of 0.5. I'm just going to do this, hopefully not run out of space. G is 9.8. The height was 0.6, I think. Yeah, 0.6. And we have 0.5. And the velocity was 3 at that point. And we plug this into our calculators. We love questions like this. And we end up with 5.19 joules. Grade 12s, don't get worried about the value you get. Look at it in context of the question. So this is a very small steel ball, 0.5 kilogram, 500 grams. That's small. 3 meters per second is actually relatively slow. And it's not very high, okay? At 0.6 meters, it's even less than half of my height, which is quite impressive. So it's actually quite low. Just going to put it out there, right? So it's actually quite low. So it's not very high, so it doesn't have a lot of potential. And it's not going very fast. So it doesn't have a lot of kinetic energy. So the 5.19 is fine. If you did this and you ended up with 3,000 joules, I would say to you that then bells need to be ringing. Because then you've got to say, does this amount of energy makes sense for the situation, all right? Be careful with those. Then they say to you, as the steel ball swings through its lowest position at C, it collides with a stationary crate of mass 0.1. Immediately after the collision, the crate moves at a velocity of 3.5. And I'm telling you now, you're looking at me going, hang on, wait, Tracy, we're doing work, energy, and power. There's no force. Now we've got something that's moving in a straight line. Guys, I did this deliberately. Energy is going to be asked with momentum. Okay? Momentum is something you did earlier this year. This part of the question is a collision that makes it momentum. Okay? And what we've got, so I'm just going to draw it here, is this ball has come to this point. Here's my crate. We had a stationary crate of mass 0.1 kilograms. They collide. Immediately afterwards, okay, the crate keeps going at 3.5 meters per second, okay, and they want to know what is the velocity of the steel ball immediately after the collision. So we want to know how fast is the steel ball going here. But now we have to say, we've got to now think about this and go, we have a little bit of a problem, because if we go back to our diagram, I know how fast the steel ball was going at part B, which was 3. That is not its velocity at C. We've now got to go, is it going slower at C, faster than C, faster than C, faster at C, not than C? Hopefully you guys realize it's got to be going faster than 3 at this point. So before I can even consider the momentum, the collision, this part, I need to work out what is the initial velocity of the ball at point C. Now, this is a pendulum. We have an object going in an arc, in a circle, okay? You cannot use equations of motion. As soon as you put an equation of motion down, you will get naught. Your equations of motion are for linear motion only. Okay, you may not use it here. If you use it here, you get naught because it's not linear. So we've now got to go find, I need velocity there. This means I'm going to use conservation of mechanical energy. They said ignore friction. Ignore friction. So at point C, all right, I know my total mechanical energy. We just worked it out. Okay? At point C, the mechanical energy at point C is 5,19 joules. We've just worked it out. The potential energy at C is actually going to be 0 because now it's reached the ground. So the first thing we're going to do is work out the velocity that it's going at. Now watch what I'm going to do. The mechanical energy at point C is equal to the mechanical energy at point B. You've got to write that statement in some way. Okay? That means my potential at point C plus my kinetic at point C is equal to 5,19 joules. Because at point C it's reached the bottom of its motion, I know potential is 0. That means I can put 0 in there straight away. I don't have to do anything else. Here, the ball is still 0.5 v squared. All right, I'm not going to do all the maths. I'm going to leave that for you. But then once we work this out, we get that v is 4,56 meters per second. Now, I've got the initial velocity of the ball before it hits the crate. I've got everything I need to do the momentum part. This was the important part here for the energy principles. From here, all right, this is just to remind you, now we're going to do total, no, let me write it with the other sign. Let's do that. Okay, so sigma momentum before, so that's before the collision, is equal to the total after. Guys, remember this funny little E that I'm doing is a Greek letter. It's sigma. I'm sure you remember that in grade 11 when you were doing molecules. I felt like you were learning the Greek alphabet. That's pretty much what you are doing. It's great. So before the collision, you have the steel ball, so we're going to call that B, and its initial velocity, plus the crate and its initial velocity. Afterwards, they're two separate objects. Okay? And before the collision, okay, we know that the ball has a mass of 0,5. It's going 4,56 meters per second. The crate was stationary, so velocity is 0. That means I can put a 0 in over there. We're very happy. We like this. Okay. Afterwards, the ball hasn't changed, but its mass, the crate, which was 0,1 meters, is going at 3.5, and we've done all the science. Now it's just a maths problem, which I know some of you don't like, but that's okay. We're fine with that, and we get this, 3,86 meters per second. Now you've got to say to yourselves, number one, does it make sense that the ball's velocity has decreased? The answer there is yes. Okay, because remember, momentum's conserved, but it doesn't mean that your kinetic energy is conserved. And more than likely, when the ball hit the crate, we're going to have sound. We're going to have, I don't think we'll have light, but we'll have deformation. I'm pretty sure it'll damage the crate, but you'll have sound and you'll have friction. So that means it's going to slow down, because remember, my total momentum must remain constant. Okay? So I'm hoping we're all okay with that question. Any more questions, or I'm just thinking I can start the next question, or
You can start it.
let's start the next question before we go for a break.
Yes.
I think, because it's a little bit longer, and it's one of those that I can hear the groans. They've seen the part of the picture, and you can just hear it. There's this collective. Yeah, that's how my grade 12s haven't done this yet, so I'm waiting for those when I get to it in my classroom. All right, so here we go. A box of mass 60 kilograms starts from rest. So over here, initial velocity is 0. Let's write it in at a height h. slides down a rough surface of length 10 meters, so that's the hypotenuse, which makes an angle of 25 degrees with the horizontal. It undergoes a constant acceleration of 2 meters per second squared. So we know its acceleration is 2 meters per second squared down, which is great. In other words, when we look at all the forces and the net force and the gravity and blah, 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 all the rest of it, it's going at 2 while sliding down the slope. So now the first thing, state the work energy theorem in words. Yay, we like this because we learn our definitions like parrots, and we go and we drive our family mad before the exam by walking around the house going, work energy theorem states that the net work done on an object is equal to the change in kinetic energy of the object. The network done on an object is equal to the change in kinetic energy of the object. Network on an object, do you see what I'm saying? You drive your family mad, but you still do well. So you get those 10-15% in your exam is aced. You don't even have to worry about it, okay? So the network done on an object is equal to the change in kinetic energy of the object. Okay. Now, draw a free body diagram to show all the forces acting on the cardboard box while it slides down the slope. I did choose this one deliberately as well because it's been a long time that on a show that I remember doing free body diagrams, okay? So the first thing we remember about a free body diagram is it's done with the dot, okay? First thing. Let's go back here, and they say there's a couple of important things. It's a rough slope. So a rough slope says to us that we have friction. Friction, very important. So the very first thing I need to do here is drawing friction. Now we've got to remember something. It's on a slope. You can't now turn this to be on a horizontal surface. Okay? So watch what we're going to do. Let's ignore the friction for now, sorry. Let's start with the fact that we know, and I'm going to go back here because they're all funny, is the very first force, there's no exception, we know which way it's going to go down, is gravity. Fg. Okay? Gravity. Now I did say draw, showing all the forces, so labels Fg is fine. Okay, that's weight. It's on a slope. Friction must always be parallel to the slope, and friction acts in the opposite direction to which it's moving. So the box is sliding down the slope, friction must act up the slope. Okay? Friction never, ever, ever, ever goes in the direction of motion. But we've only got 2, it's worth 3 marks. Your third mark is your normal force. And your normal force will go up here, and that's an N. And when you look at, if your object's, there's the slope, there's my box, your normal force is always perpendicular to your surface. Always, always, always. So this angle here should actually be 90 degrees, and your gravity acts perpendicularly down. Okay, be careful. Don't go and change this so it's on a horizontal plane. Okay, and I think that's a very good place to take a break because the next set of questions here is all the calculations.
And I have plenty of questions.
Have we got plenty? All right, brilliant. Okay.
And great comments. Well, guys, stay tuned because after the break, I'll take some of your comments, your questions, and tell you more about another exciting competition or other competitions that you should get yourself on in order to win big. Stay tuned. Welcome back, guys. Now, if you're thinking about accommodation and studying next year, as a matriculant, you should think about accommodation. So we're giving you 1 year's free of accommodation at any of South Point's accommodation. All you need to do is to fill in the entry form that's on our Facebook page, and it gets you in. So, guys, what are you waiting for? Don't waste any further more time because next year you might just be stressing about accommodation. So here's an opportunity. Otherwise, Tracy.
Wow. Yes. Love it. Love it. And enter that competition, grade 12. Seriously, accommodation for varsity is so expensive.
You don't want to be accepted and then
can't
don't
go.
have a place to stay.
Or you can't go because you can't have nowhere to live. So really enter it. It's worth the chance.
Of course.
Anyway, okay, so we've got some questions, have we?
Got some questions for you.
Okay,
and
let's see if I can help. Yes.
Try to go over them very, very fast.
Yes.
Okay. Lovely chapter. Okay. Pretty evidence say lovely show. Yeah. She is flowing. Tracy is flowing. Paris, shut up, Mtombieni. says, okay, thank you, Mindset. I really enjoy learning with you guys. And Tawasimnya says, how did you get the velocity in the question where you used the sigma sign?
Okay, let's do that one quickly. Over here, where did I get? Okay. The way I got the velocity, okay, sweetie, is I don't have the calculator up, it's my own fault. So you first have to multiply the 0.5 and the 4, actually I can write it out, watch. So I'm going to take this part over, so we're going to go 0.5 times 4.56, and I'm going to minus the 0.1 times 3.5, okay, and that gives me 0.5 for the velocity. And then, once I've worked out the addition part or the subtraction part, I'm going to divide by 0.5 on both sides, and that'll give me the velocity. Okay.
Awesome. Okay, here's another one from Jimmy Rappel. I just love Miss Tracy. Watching physical sciences with my mom, so loving this topic. Everyone is watching with their mom.
I love these mothers.
Where are the dads? Okay,
no, I
the
think
dads
the mom is like going, come.
You're
going to watch now, learn. Before she like smacks you hard. You know what I'm saying? I think I see it. I've got parents' evening next. It's the mothers who come, and it's the moms I'm scared of, eh? Yeah, it's the moms.
Let's not go into parenting.
Let's not go there.
Let's not go there. Next one, Jimmy. Big shout out to you. Rose Mwana Maha Malefo says, where do we use a 0,180 or 270 and 90 degrees?
Okay. In this one, you're never going to use 90. Well, you might use 90, but you're never going to use 270, ever, ever, ever. With the 0 and the 180, when I do the next question, when we look here at the bottom of this, they now ask me to calculate kinetic energy, work done, all of these. Here I'm going to use the 0 and the 180. It all depends on the force. So I am going to do that. Hold that question for me. I'm not ignoring you, but we are going to, and in the next question, I'm going to show you where to use the angles. Okay, so just hang fire.
Okay.
I promise we'll get there.
Quickly, a tweet from Kelvin K_SA. He says, will it be okay if I still put the normal force perpendicular on the object as always as if it was moving in a horizontal line?
So if I'm understanding the question right, you want to put the, and I'll do it in another color, if you put the normal force going vertically upwards like that, then no, not at all. Okay, because it's not moving horizontally. It's got to be perpendicular to the surface. All right, always, always, always. So it can't go horizontally, so no.
Okay.
Yeah.
Last one on degrees, Quintin Mungalo.
Yeah.
Do you always use 180 degrees when calculating friction, or the other forces that need 180 degrees?
If it's opposing the motion, so if the force that you're calculating or the force you're using is in the opposite direction to which the object's moving, yes, you use 180. Always. No exception. Good.
Good.
Okay. So, next part of this question is calculate the kinetic energy of the box using equations of motion. So now they've been specific here, and they want you to use equation of motion for this reason. This is what they're trying to tell you is you can't use principles of energy principles here because we don't know what H is. So I can't go, the mechanical energy here is equal to the mechanical energy over here. We can't do that, okay? Because first of all, there's friction, so mechanical energy isn't conserved. But because they gave me acceleration, they've given me initial velocity, and I know the distance, I've got to use the 10 meters, I absolutely can work out final velocity. So what I would do here is, and they gave me distance, so let me just do it. So we got VI, which is 0. VF is what I'm looking for because I want to work out kinetic energy, so I need to use VF. A, they told me, is 2. Delta T, I don't know, but delta X is 10. Guys, I can use delta X now because it's moving almost horizontally. If you use delta Y, I'm pretty sure they would accept it. So we look at this and we go, fine. We then go onto our information sheet and we find the equation that suits this. It's not any of the ones with time in it. It would have to be VF squared. Ooh, that is not a square. VF squared equals VI squared plus 2A delta X. Okay, so VI is 0. we have 2 times 10. No, I'm lying to you. 2 times 2 times 10. Guys, they chose these numbers deliberately because 2 times 2 is 4. 4 times 10 is 40. And then you would square root the 40 to get VF, and we get 6,32 meters per second. But I haven't actually worked out the answer yet because they said calculate the kinetic energy. So I'm going to go, well, EK equals a half mv squared. So this is a half, and we go back to the question, and okay, it's a 60 kilogram block, so it's quite heavy, and this is 6,32 squared. But we know we don't even need to worry about this because we know, and in fact I can do this in my head, because from here I know that 6,32 squared is actually 40. We worked that out earlier, so this is the same as going a half times 30 times 40, and we would end up with 1,200 joules. Grade 12s, use your calculators, okay? I have friends who call me slightly autistic. It's a bit rude, I know this, but I can do numbers easily in my head. It's just one of those things. Please, calculators. Okay, don't try and be brave and big and whatever you call it. Don't. That's why you have a calculator. Okay, now, oh, look here. Calculate the work done by the box, on the box by the gravitational force. So we want work done by gravity. So we're going to use F. Now we've got to make a decision because we can use Fg delta x cos theta. Okay? Now life gets interesting. Okay? Because if we look at my system, if I'm going to use Fg, I need to know what that height is. Okay? If I want to use Fg as it stands. And now we've got to say to ourselves, can I work out that height? Because that would be delta x, okay? Because we're going to do this the easy way rather than the difficult way, which I quite like personally. It's just one of those things. Okay, so now we're going to say, fine, I want opposite and hypotenuse. All right? So if I've got the opposite side and the hypotenuse, that means I need to use sine. Sine 25 degrees is equal to the opposite side over the hypotenuse. So the height that this is going to go through is 10 times sine 25 degrees. I'm looking at vertical height. Now the reason why I'm doing vertical height is for my theta in cos. All right? So now we go, fine, let's go back here. All right? And we're going to go, well, Fg is calculated using mass times gravity. Okay, Fg equals mg, you know this. Okay, so now I'm going to go, mg means I'm going to go 60 times 9,8. Delta x, we just worked out, is 10 times sine 25. Because now we've got to decide on an angle. I have gone vertical height down. The distance is vertically downwards. So the angle, because it's going vertically downwards and gravity is going vertically downwards, is 0. Okay? Is 0. And when we plug this into our calculator, we get 2,485 joules. It's nice and big. It's a big object. Okay? So what I've done here, and this is important, this delta x was the vertical height. And I went back and used trig. There's no way around using trig in this. I'm sorry, grade 12s, I wish there was. I really wish there was, but there isn't. So this becomes a straight substitution. All right? And the 0, because it's going vertically downwards, and the gravity is vertically downwards. Same direction. Okay. So, now it says, Oh, look. The work done on the box by the frictional force using the work energy theorem. Okay, so net work says using the work energy theorem. So we know net work equals change in kinetic energy. That's where we're going to start. Okay? Now, the net work done is going to be equal to the work done by gravity, because gravity does work, plus the work done by the friction. Don't minus here, plus. Okay? My change in kinetic energy, so it's final kinetic energy minus initial kinetic energy. So now we're going to go, okay, fine, let's look at what we've got. Work done by gravity, we've just worked it out. Okay, let's see what it was. It was 2,485. We don't know work done by friction. Oh, final kinetic energy, we did it. Look, 1,200, we did it earlier. They led us very nicely. But what's the initial kinetic energy? So now we're going to say, okay, let's just go. We go back to the beginning, and they said to us, oh, look, initially at rest. That means 0 kinetic energy. If it's at rest, no kinetic energy, because V is 0. All right, so this actually is so much easier than it looks like. So over here, this becomes 0. And look at that, this is a math sum. Because now I've got to solve for WF, and what that means is it's going to be 1,200 minus 2,485, which gives me negative 1,285 joules. And you know what? You leave it as negative. It's work done by friction. It must be negative. Okay? Your final answer here must be negative. Because if I needed to work out the work done by friction and I knew the frictional force, my theta is 180 because it's in the opposite direction. And in fact, I think that's the next question, because now it says, what is the frictional force? Well, work done by friction is my frictional force, delta x cos theta. Work done by friction is minus 1,285. We want the frictional force. According to my diagram, it went 10 meters down the slope. I'm going on the slope. I can't use the height now. Okay, so when I go back here, I can't use the height, grade 12s. I've got to use the slope because the friction acts on the slope. All right, so it's got to be where the friction acts. So let's go all the way down. That could get a little bad on the eyes. So that's 10. And theta is 180 because the object's going down the slope and friction's acting up the slope. Opposite directions. This is 180. And this, so we get minus here. Cos 180 is negative, so this is actually negative 10 times your frictional force. So that means your frictional force is 128,5 newtons. Okay? If you had not given this as a negative, you would have ended with a negative answer here, and that's a problem. Okay? So be careful, because your angles take those negatives into account. So be careful with those ones. All right? Do you have lots more questions, or do you have time?
I've got questions for
Okay,
you.
let's do those, because I do have another question, but we can...
All right.
Yeah.
Here's one from Menzi, at Menzi Heaven. He says 2.3.2.
Yes.
Or perhaps let's start with 3.2.1, because there was a question on that one.
Okay, yes.
From Nomatam Sanga saying, Mem Tracy,
Yes.
why did you say we cannot use equations of motion, but it seems like you used one in
Okay.
2.3.1?
Okay. In question 1, I said you couldn't use equations of motion because it was swinging. Okay? And with a pendulum, the motion isn't linear because it's going in a circle. So the direction of the object is constantly changing. With this one, this is still linear motion because your object's going in a straight line. It is going at an angle, but it's going at the same angle the whole way through. So I can use equations of motion. And they actually said to me, use equations of motion. So I didn't have a choice. Okay, so with a pendulum, something that swings in an arc, in a circle, no equations of motion. If it's going in a straight line, absolutely you can use equations of motion.
Okay, nice one. At Menzi Heaven says 2.3.2.
Yes.
Why do you use 10 sine 25 instead of 10 itself, please?
I didn't use tan, I used sine, okay? And I'm not using tan because I'm not using the adjacent side of my triangle, okay? So I've made quite a big mess of this triangle. So if we look at this triangle again, all right, the thing is, this is my angle, okay? The 10 meters is the hypotenuse of the angle, and h, the height that I'm looking for, is the opposite side because there's the triangle I'm using, okay? You're very rarely going to use tan. You're going to use sine or cos. So because this was the side I was looking for, and it's opposite the angle, I used the sine function. Okay, so I'm not really going to use tan, and I have to multiply by 10 because sine 25 is h divided by 10, and I want h on its own, and that means I've got to times both sides by 10. Okay?
Okay.
Yeah.
Put evidence says, during an exam, will I get full marks if I write a formula, substitution, then answer?
Absolutely. If your formula's right, your substitution's right, and your answer's right, absolutely. As long as, be careful though with the answers. If you need to put direction, okay? But yes, that's the best way to do it. Formula, substitution, answer.
Okay,
Yeah.
Samsung again says, what do they mean when they say a frictionless object or a pulley?
All they're saying is you can ignore friction. So this one settles on a rough surface, so that means friction opposes the motion. If they say it's frictionless, if they say it's a smooth surface or it's a frictionless pulley, just means you can ignore friction. It's to make the calculations easier. That's why they do it. Okay.
Okay.
Yeah.
I just thought this comment is awesome. Your show is really amazing and awesome. I feel like I'm in a normal class when watching. And by the way, you have awesome teachers, especially the one teaching. That's from Cosmos from Zambia. Thank you so much.
From
Cosmos.
Zambia? Are you
Yes.
watching us from Zambia?
Yes.
That's impressive. I didn't know I was international. I feel good. You're welcome, Sweet Pea. That's the purpose of the show.
Now you know. Ex Obakwe Faith Matimela says, at first I couldn't understand a thing, but then I watched Mindset, everything became really good. Thanks,
I'm so
Tracy.
glad.
You're the best.
You are so welcome. This is why I do it, actually. Yeah.
Tracy _ brilliant, the human calculator. That's what Tabo said.
I don't want to
Tracy.
start that one. but-
Tracy's a human calculator.
All right.
Right, nice. I think you've explained this one, but I think you can go back. Hulani Gracious Mapoli says, can you please explain why you used cos 0, not cos of 25?
Okay, because, and that's actually a very good question, because I've worked out the vertical height here, okay, I've already used the 25 degrees in my calculation. I don't want to use it again, okay? I would only have used cos 25 if I was using, and even then I probably wouldn't in this case, with the 10 meters. I've already used the 25 degrees. You don't want to use it twice. Okay, this angle will only get used once in the calculation when it comes to your forces. So because I've taken it into account, I now am working with a displacement that is parallel to the force. That's why I used cos 0. In fact, we want to get to that point where we can either use 0 or 180. So we want to get rid of those angles as soon as we can. Okay.
Last one.
Yes.
Asana Mnyandu says, Abraham, please ask Tracy, will I be wrong if I write my final answer, a frictional force, as positive, and then indicate the direction of this force instead of leaving it as a negative?
You will be wrong. If down the bottom here, you ended up with a positive answer here, positive answer with a negative answer and then changed it, the problem here is going to be the substitution is incorrect because your work done by friction is negative. So that's where you'll lose your mark. You'll get a mark here, and this was worth 3 marks. You'd get 1 out of 3 because your substitution is incorrect. So unfortunately, I know what you've done, but your substitution's incorrect. And we're running out of time, so I've got to say bye-bye, and I'll see you soon.
Thank you so
before I
much.
get mine done.
Thank you so much, Tracy. Thank you guys for watching this show. It's been awesome. I hope you've learned so much, just as we have. Remember, we also have the Be a Bright Spark competition. So enter right now if you think you are that bright spark and you could win a Chevy Spark L. Guys, thank you so much to the Department of Basic Education for making sure this show is possible for us. We love you. Peace.